Swayam Prabha. Digital India. Educated India.
Hello everyone. In this lecture we will continue our discussion on polynomials and discuss some more concepts. First we will discuss a very simple result which is a consequence of a result that we have studied before for general PIDs, principal ideal domains. So, the result says that if we take any polynomial f over a field f, then fx by f, this is the quotient ring of the ideal generated by the polynomial f, and this quotient ring is a field if and only if the polynomial is irreducible, f is irreducible. So, this result follows from a more general result for PIDs. For PIDs, we have seen that if you take any element C, the PID, the quotient ring of the ideal generated by the element C is a field if and only if C is a prime element. And for polynomials, first of all we know that fx is a PID. So, R equal to fx, and prime polynomials basically mean irreducible polynomials. So, it directly follows from that result. Now, we will see some examples. This is very important result for us because this is how we will construct finite fields. This is the most popular way of constructing finite fields. You take one finite field, for example, we already know finite fields of the form Z3 or Z2 like that. So, which is Zp in general, for p is a prime number. If p is a prime number, the integers modulo p, which has the element 0, 1, 2 up to p minus 1, and addition and multiplication are modulo p, we know that this forms a field. And once we have this field, we can take any polynomial over this field and take this Zp x polynomials modulo the prime polynomial f, and that will give us another field which is a bigger field. It is an extension field of Zp. Now, we will need only one thing for this, which is an irreducible polynomial over this field. So, we need to have irreducible polynomials over this field, then we can construct extension fields of this. So, we will see some examples. We have already seen that the field of complex numbers can be seen equivalently as the quotient ring of a polynomial, which is x square plus 1. So, you take the real field, you take polynomial ring over the real field and take one polynomial x square plus 1, and we know that this is an irreducible polynomial over real numbers, right? And so this does not have a root, and this is a quadratic polynomial. So, it also means that it is irreducible, and so we can take this quotient ring and this will be this is a field. We have explicitly proved that this is a field before, but in general any irreducible polynomial if you take here, it will give us a field. So, this is one example. We have also seen similarly we can construct take Z2, which will also denote by F2 because it is a finite field of 2 elements, and take the polynomial ring F2x and take an irreducible polynomial, let us say x square plus x plus 1. What will be the elements? Its elements are basically the cosets of this ideal, the ideal generated by x square plus x plus 1. So, which are the coset of 0 is the ideal itself. So, we will denote it by 0 over bar, coset of 1, coset of x, coset of x plus 1, and that is all. First of all, we are considering Z2 which has 2 elements. So, coefficients can be of only 0 and 1, and if you take any higher degree polynomial, you can divide higher than 1 degree, then you can divide it by this polynomial x square plus x plus 1, and the remainder we get, that will be in the same coset, and that remainder will have degree 1 or 0. So, it will be one of these, right. So, if you take any polynomial, for example, if you take x cube plus 1, right, where is you may wonder where is the coset of this here, it should also be here, but the point is that this is equal to one of these also, this is equal to one of these 4, because if you take x cube plus 1, you can divide it by x square plus x plus 1, you get first x, then you get x cube plus x square plus x, and then if you subtract or add, because modulo 2 addition is same as subtraction. So, you get x square plus x plus 1, so you get 1, and then x square plus x plus 1, that is it. So, the remainder is 0 in fact. So, it is in the ideal, and this is in the ideal, and so x cube plus 1 is in the ideal. So, it is same as this. So, it is easy to see that this is an irreducible polynomial. For quadratic polynomials, it is just sufficient to check that there are no roots. You put 0, you evaluate, you get 1. You put 1 in place of x, you get 1 plus 1 plus 1, which will give you also 1 modulo 2. So, neither 0 nor 1 is a root of this, and the only way to factorize a quadratic polynomial is into non-trivially is in linear factors, which means that they will have roots, and these things we have not discussed, but we will soon discuss that roots mean that it should have linear factors and so on. Now, we can take any irreducible polynomial of higher degree. This is of degree 2. There are irreducible polynomials of higher degree over Z2. For example, again you take F2 and take Fx equal to x cube plus x plus 1. Again, it is a degree 3 polynomial. If there is a factorization, then there must be at least one linear factor, which will mean that there is a root, right. And so, we can check for a root. Is there a root? If you put x equal to 0, we get 1. If you put x equal to 1, again we get 1. So, no roots for this polynomial, neither 0 nor 1 is a root. So, how many elements are there in F2x quotient x cube plus x plus 1? 0, 1, x, x plus 1, x square plus 1, then we have x square plus x, x square plus x plus 1, 8 elements. Now, we may see that these 8 elements are exactly all the polynomials of degree less than 3, where 3 is the degree of the irreducible polynomial we have taken. So, how many polynomials are there of degree less than 3? You can see there can be 3 coefficients: degree 0 coefficient, the constant term, degree 1 and degree 2. So, all polynomials of degree less than 3 are of the form a naught plus a 1 x plus a 2 x square, and each of these coefficients a naught, a 1, a 2 are binary, they are from f2. So, they are either 0 or 1. So, how many combinations are possible? There are 2 power 3 combinations, there are 3 of them, each of them can be chosen in 2 ways. So, there are 2 power 3 elements. So, this is a field and this has 3 elements. So, we denote it has 8 elements, 2 power 3 elements. So, we denote it by f 2 power 3 or f 8. So, we have got a field with 8 elements. Similarly, we can take for example, degree 4 polynomial x 4 plus x plus 1, x 4 plus x cube plus 1, this is also irreducible, x 4 plus x square plus 1, is this irreducible? We can check that this is actually not an irreducible. Can you find a factor of this? Well, I leave that as an exercise. So, in general you can see that if you take a polynomial of degree d, f x is of degree d, if degree of f is d, then you will have, if you take a finite field with let us say z p and f x is f in z p x, it is of degree d, then the quotient will have how many elements? The quotient field will have p power d elements. So, we will end up having an extension field of ZP with so many elements. Okay. So, we will denote such a field as f p power d. Now, we already talked about roots, but we will now formally define roots of a polynomial. If f is a polynomial, an element a in f is called a root of f if f of a is 0. Okay. And here is a simple result. If a is in f and f is in f x, then a is a root, that is f of a is equal to 0 if and only if x minus a polynomial divides f x. Why is this? It follows easily from the division lemma, which says that any polynomial f x. So, f x can be divided by x minus a. So, we just divide f x by x minus a. What do we get? We get a quotient. So, we get a quotient. So, x minus a times the quotient and a remainder r x, okay, such that. So, this we can do for any two polynomials, in this case f x and x minus a. So, that degree of r x is less than the degree of x minus a. Now, what is degree of x minus a? It is 1. So, degree of r is strictly less than 1, which means it must be a constant, right. So, in other words, r x is not a polynomial at all, it is just a constant, and you can simply write it that way. Now, this is because we are dividing by a linear polynomial here. So, it is a constant r, it is not a polynomial, it is a constant. Now, what we want to show is that if a is a root of f x, then r should be 0. Okay. Now, why is that? We simply put a on both sides. So, what do we get? F of a is a minus a times q x plus r, q of a plus r. Now, this is equal to 0, f of a equal to 0 because a is a root and a minus a equal to 0. So, what we get is r equal to 0. So, in fact, this is if and only if you can see this follows both way. Now, there can be a root which is there multiple times in a polynomial. By that we mean that you may be able to divide f x by x minus a multiple times. In such cases we say that that is a multiple root. Okay. So, multiple root. So, a is in f and f a is 0, a is a root. Okay. Then we say that a is a root with multiplicity k if x minus a power k divides f x, but x minus a power k plus 1 does not divide f x. Okay, so, f x has x minus a kth power inside it, but not anymore. Then we say that the multiplicity of a is k. If k is 1, we say a is a simple root. If k is greater than 1, we say a is a multiple root. Okay. Now, here is again a result which is easy to prove and quite believable, which says that all the roots of a polynomial, you have f x which is a polynomial over f, all the roots, the number of roots counting multiplicities is less than equal to the degree of the polynomial. So, the number of roots counting multiplicities is less than equal to degree of f. Okay. What does it mean? It means that suppose these are the roots b1, b2, m. These are the roots of f and the multiplicities with k1, k2 up to km, these are the as multiplicities. Respectively. Okay. K1 is the multiplicity of B1, K2 is the multiplicity of B2, etc. Then what this is saying is that if you counting the multiplicities, B1 is a root K1 times. Okay, it's had multiplicity K1, it means it is a root K1 times of f. So, we count the, it is K, there are K1 roots basically which is the same as B1. So, k1 plus k2 plus all these roots km, this is less than n, the degree of f. Okay. In fact, what we can say is that, in fact, then we can say then this polynomial x minus b1 power k1 x minus bm power km divides fx, and in particular as a result this holds, right. Clearly, if this holds, then this will also hold, because if you simply take the degree of this, so fx is this times something and degree of this is this side. So, degree of f is this plus something. Okay. So, we want to prove this. The proof of this is quite obvious, because b1 has multiplicity k1, we already know that x minus b1 power k1 divides fx. Similarly, all these x minus bm power km divides fx. So, because these x minus b1, x minus b2, all these are prime irreducible polynomials, are irreducible. Basically, what we are saying is that these are factors in the unique factorization, unique canonical factorization of fx into prime factors. So, fx, the canonical factorization of fx looks like x minus b1 power k1 times x minus bm power km, and there may be some other factors which are irreducible, some other factors which are of higher degree than 1. So, you can have some p1x power, let us say alpha 1, and ptx or alpha t and so on, some more factors. So, at least these factors are there, that is the more important part, right. So, this whole thing divides fx, this is what we wanted to prove, and that follows from here, and the consequent this result also follows. Okay. Now, we will discuss a very important and interesting concept called formal derivative of polynomials. For any polynomial fx, let us say a n x power n plus up to a naught, let us say a 1 x plus a naught over f x. We define its formal derivative as n a n x power n minus 1 plus n minus 1 a n minus 1 x n minus 2 plus up to a 1. Now, it is exactly the same formal derivative that we it is exactly the derivative of a polynomial that we know, except remember that we talked about previously, we knew about derivative of a polynomial as a function, and those functions are either real functions or complex functions, but we are talking here about general polynomials over arbitrary fields, including finite fields, which are very discrete in nature. So, these are not continuous functions, these are in fact just polynomials over, let us say, binary polynomials. If you put values, you can put values only zeros and ones, and you get zeros and ones. So, there is no continuity, it is a discrete space. So, the input x value of x itself has only, there are only two values, and the output the value of the function also only 0 or 1. So, there is no concept of continuity there. That is why this derivative, what we have done is we have taken the same expression that we know to be the derivative of polynomials for the continuous case, but we are just saying that this expression itself is defined as the formal derivative of f x. Okay. And we will see that this also satisfies some nice properties like derivative, though it does not have that interpretation as a the slope of a function or something. So, for example, one can prove this multiplication rule for formal derivatives. If you take two polynomials f x and g x, they are the formal derivative of their product is same as f x g prime x plus f prime x g x. This can be proved easily by simply using this as the definition. We will omit the proof here, just need to write down in the summation form these on left hand side as well as the right hand side and show that they are the same. Okay. One consequence of this result is that if we have a root of a polynomial, then this is a multiple root of f. Multiple root of f x if and only if it is a root of f and f prime, both f and its formal derivative, then it is a multiple root. First of all, note that we will consider only b to be a root, and then we will talk about multiple root or simple root, because if b is not a root at all, then it is not even root of f. So, obviously, both of them are false, right. B is not a multiple root and it is also not a root of f. So, it is not a root of f and f prime, it does not satisfy this condition. So, let us consider b to be a let us assume that b is a root of f x, that is f of b is 0, which also means that f x is divisible by x minus b. So, it is of the form x minus b times some polynomial, okay, times let us say g x. Now, we will prove the forward direction, that is, we will assume that b is a multiple root, then we will show that b is of course then a root of f, but we will show that b is also a root of f prime, the formal derivative. So, if it is a multiple root, we know that its multiplicity is at least 2. So, f x is in fact x minus b square times some polynomial h x, right. Then what is its formal derivative? We use the multiplication rule. So, we take the derivative of the first part 2 times x minus b, that is the derivative of this part, and h x, plus we keep the first part intact and take the derivative of h x. So, you get this. Now, you can see that x minus b is a factor of this 2 h x plus x minus b h prime x. Right. So, clearly x minus b divides f prime x. So, b is a root of f prime x. Now, the other direction is also simple. Suppose b is not a multiple root, it is a simple root of f x, then we know that f x can be written as x minus b times g b, where g x, where g of b is non-zero, it is not 0. Now, we can again take the formal derivative f prime x using multiplication rule, we get g x plus x minus b times g prime x. Now, we put b on both sides, so we get f prime of b is g of b plus 0, which is then g b, but g b is non-zero. Note this, g b is non-zero, so this is non-zero. So, we have that formal derivative evaluated at b is non-zero, which means b is not a root of f prime x. So, this gives us a nice way to compute, find out if a given element is a multiple root or not, given root is a multiple root or simple root. You simply compute the formal derivative and see if it is a root of that formal derivative also. What if we want to compute, if we are given a polynomial and we want to find out if it has any multiple root at all? So, what we will do, we will take f, we will take its formal derivative, we will compute their GCD. Okay. If the GCD has any root, then we know that it has a that is a common root of both f and f prime, and that is a multiple root of f. Okay. Now, we will discuss a different another important concept called interpolation, and there is a nice result called Lagrange interpolation formula. What does it say? Well, what we want to know is, suppose we are given, even for real numbers, this is a very important concept. You have, let us say, certain values at certain places, you want a polynomial function, you want a function to have certain values in these positions. Let us say these values here, these are a1, a2, let us say a0, a1, a2, a3, like that up to a n, and you want the values of the function at these places to be, let us say, b0 here, b1 here, b2 here, b3 here, maybe b4 here, and so on, bn here. You want a function that is like this. Like this. So, you want to interpolate this function so that we get a polynomial function of the smallest degree, and so these values are given, a0, a1, an are given. There are n plus 1 values, and the value of the function should be b naught, b1 up to bn. And now the result says that there exists a unique function, polynomial function f of degree n plus 1, such that f of a I equal to b I for I equal to 0, 1 to n. At all these points the values are as required. There, if you consider degree n plus 1 polynomial, there is a unique degree n plus 1 polynomial satisfying this condition, okay. And that polynomial is given by I equal to 0 to n, b I k equal to 0 to n, k not equal to I, x minus a k by a I minus a k, this. Now, this looks complicated, but it is quite a simple thing. So, let's understand the structure in this polynomial. It is the sum of some polynomials. You see that it is a linear combination b I times this polynomial, b 1 times this polynomial for I equal to 1, b 2 times this polynomial for I equal to 2, and so on. So, it is the sum of some polynomials. Now, each polynomial, if you see, so it is basically it is of this form I equal to 0 to n b I f I of x. And now, this f I is a very simple type of function. F I x, f I of a j, all these points, right, these points a naught, a 2, a 1, a 2, all these a j, at any of those points if you compute f I, what you will get is 0 for all values other than j not j equal to I. So, 0 if j is not equal to I, and 1 if j equal to I. So, this is a function which has the values at, let us say you take f1, f0, f0 has one value at a0, the value is 1, and at a1 the value is 0, a2 the value is 0, etc., zeros. Everywhere else it is zeros. This is f0. Now, f1 is zeros other than and 1 at a1, all other places zeros, okay. And this is f1. Similarly, f2 has value 1 at 2, a2, all others the values are zeros. Now, what this is doing is this is taking a linear combination of these functions, so that the value here becomes b1, b0, value here becomes b1, value here becomes b2, and so on, and that is what is required, right, these values. So, this is how the interpolation is done. So, now how do you compute, how do you get a function like this which is of degree n plus 1, degree n, okay. So, if I needs to have value 1 at a I, okay, all others it should have value 0. So, what we do is we take the polynomial x minus a1. So, let us suppose we want to do this for f2, we want to get f2. So, it should have value 1 at a2, all others at a0 it is 0, at a1 it is 0, at a3 it is 0. So, what we do is we take x minus a0, x minus A1, and then x minus A2 we omit, we take x minus A3, x minus A4 and so on. Now, this polynomial has value 0 at all other places other than A2, and A2 it has some value which is A2 minus A0, A2 minus A1, A2 minus A3, the product of these. So, we divide by that product A2 minus A0, A2 minus A1, A2 minus A3, all these, so that the value at A2 becomes 1, and at all other places it is anyway 0, because if there is a x minus ai in the numerator. So, these functions, this is basically that. Okay. These component functions fi are exactly that. So, this is how we do interpolation. This is called Lagrange interpolation formula. If you have n points, you can assign arbitrary n values and you can get a polynomial of degree n minus 1. Okay. Now, that polynomial is unique, okay, degree n, because you can see that here the product is k equal to 0 to n, k not equal to I. So, component functions also you see that one term is missing. So, the degree is n. Now, there cannot be two functions with the same values at these specified points of two functions of degree n. Why? Because if you have two functions f and g, then f minus g will have value, they will have the same values at those a0, a1, etc., those n plus 1 points. That means f minus g polynomial, which is a non-zero polynomial, will have n plus 1 roots, and it is of degree equal to n, degree less than equal to n, because both f and g have degree less than equal to n, and this cannot happen. A polynomial of degree n cannot have more than n roots. Okay. We have seen that result in this lecture itself. Number of roots counting multiplicities is less than equal to the degree of the polynomial. Okay. So, now we will finish with one simple observation, that just like we can construct rationals from integers by taking rationals like 2 by 3 and so on, and that set of rationals forms a field, okay, the Q, the set of rationals forms a field. Similarly, we can do that for integers, for polynomials also, and the rationals of polynomials, the set is denoted by f in fx, the brackets are like this. This is the set of rationals of polynomials fx by gx, where f and g are polynomials and g not equal to 0. And this is also, one can prove easily that you can define addition, multiplication, the standard fashion, and you can show that it forms a field. We will not go into the details of these, but it gives another way to construct fields from polynomials. Okay. So, it is the field of rationals of polynomials. Thank you.